Can you see my mouse, my cursor?
Yes.
Okay.
So we will have a question and share probably at the end of your talk. And
that's good.
Yeah, and we can also take some questions in the chat box. So if any participants have the questions or any clarification, they can write on the chat box itself.
Okay.
So good afternoon to everyone. I welcome you for this third talk of the third talk of this webinar series. Let me first introduce Dr. Duncan, today's speaker. It's really my great pleasure to introduce Dr. Duncan. He has been in IST 2 times before this webinar. So thank you very much for being so generous for your kind consideration to be in IST webinar. So Dr. Duncan is Droplet Measurement Technologies Director of Science Program. His primary area of expertise is in aerosol cloud interaction, cloud microphysics, and weather modification. Duncan's work at Droplet focuses on partnering with scientists and research laboratories to design science programs, develop funding proposals, and ensure that program activities are strategically conceived and executed to a high level of scientific accountability. Dr. Duncan earned his PhD in engineering with a focus in aerosol microphysics from University of Denver and master degree in atmospheric science with a focus in aerosol cloud interaction from Texas A&M University. Prior to joining Droplet, Dr. Duncan worked at the National Center for Atmospheric Research, NCR, conducting atmospheric science field program using scientific instrumentation to investigate aerosol cloud interaction, cloud and precipitation microphysics, new particle formation, and weather modifications. He has participated in over 30 field campaigns, including campaign in US, Europe, Australia, Peninsula India, and Asia. I request Dr. Duncan to deliver his webinar. So Dr. Duncan, over to you.
Thank you very much, Dr. Sinia, for this introduction. Of course, it's my pleasure to be with you here today. Good afternoon to all of you. It is very early in the morning here in Boulder, Colorado, and the temperature outside is -10 degrees C. So very different from the temperatures that you're currently experiencing. You also have snow on the ground. Anyway, thank you for being here. What I would like to share with you today is some work that I did a few years ago in studying aerosols in the upper troposphere and the lower stratosphere. What you see here in this first image is a picture taken from a high altitude research aircraft that is flying in the lower stratosphere. And you see almost the curvature of the Earth. So this is at about 18 kilometers. And this is the area in the mid-latitudes where the lower stratosphere occurs. The aerosols here are still being studied because there's very few data that describe aerosol processes in this very important region. So why is aerosol in the upper troposphere, lower stratosphere very important? We'll discuss that today in the context of these new particles that form through processes of new particle formation can end up becoming cloud condensation nuclei. A lot of work has been done in understanding the fate of these aerosols once they form. So these aerosols form by a process called new particle formation, or NPF. And a recent study, including some of the work that I have done in identifying these newly formed particles, was published in Nature just last year, where we found that NPF persists at all longitudes as a global scale band in the tropical upper troposphere, covering about 40% of the Earth's atmosphere. And these processes are globally important as sources of cloud condensation nuclei. So these particles act as a seed for cloud particles to form. So in order for us to understand this better, we ask the questions: when, where, and how often does NPF occur in the UTLS? What is the role of air mass origin in the tropopause layer in the formation of new particles? What is the impact of deep convection on NPF in the upper troposphere? And what is the impact of newly formed particles on the concentration of potential CCN? And in this paper, you see this nice cartoon, this nice figure that shows that deep convection can have an important role in producing the conditions that are suitable for new particles to form in the upper troposphere. Then these new particles continue to grow, and they seed clouds by forming CCN in the boundary layer. So this process is a very important process also for boundary layer clouds. So most of the data that I'm going to show you today is taken from the campaign called MACPAX, which was conducted in 2011 with a high altitude research aircraft owned and operated by NASA. And this experiment was conducted in the northern mid-latitudes. But there's also data from a subsequent campaign with the NASA DC-8 from a campaign called Seekers in the southwestern US. And then finally, a global campaign called ATOM, where I show a snapshot of data that was collected globally using one of our instruments that we build at Droplet Measurement Technologies called the UHSAS, Ultra High Sensitivity Aerosol Spectrometer. These measurements in the UTLS are sparse and required specialized high-altitude platforms. The challenge with studying aerosols in the UTLS is that there's very few instruments that perform well at this high altitude, and also there's very few aircraft that operate at this altitude. So what is new particle formation? New particle formation is the process where SO2 and OH combine to form sulfuric acid vapor. Then sulfuric acid vapor combines with water through the process of binary nucleation to form what we call clusters. And these clusters are very small in size. They're sub 1 nanometer in size. And several clusters need to combine together in very favorable conditions where you have high concentrations of stabilizing vapors and few pre-existing aerosol particles, because pre-existing aerosol particles act as condensation sinks for the stabilizing vapors. So there's a competition between the newly formed particle, this cluster that you see here, and the stabilizing vapors that allow this reaction to proceed. And the stabilizing vapors may condense on the pre-existing particles, which could compete with this process. But if the conditions are right, then the sulfuric acid vapor and continues to condense on the particles, and the particles continue to grow. And then once the particles grow, they can increase the aerosol mass. And once the aerosol mass increases, there's a whole set of microphysics that it comes into play in terms of adding the number of CCN and adding the number of ice nuclei. If we follow the path of the newly formed aerosol particles adding the number of CCN, these would then add the number of droplets in clouds, increasing the number concentration, which also could modify the hydrometeor concentrations, which then impacts the cloud optical depth, the cloud albedo, and the Earth's radiation budget. The same applies for ice nuclei. If these particles act as suitable ice nuclei, these are going to increase the ice particle concentration, which increases the ice hydrometeors within clouds, which then modifies the precipitation, the cloud optical depth, and the cloud albedo. The issue here is that we can only measure aerosols larger than 3 nanometers in size. So there is a challenge with observing the process of new particle formation. How does new particle formation play in terms of cloud condensation nuclei? What you see here on the left is a modeling study by Mericanto et al. At Leeds in the UK, where they simulated various aerosol formation processes globally. What you see here in panel B is the contribution of aerosols to CCN as primary particles. And you see that these primary particles dominate the CCN over land due to pollution, forest fires, and dust, and then over the Southern Ocean due to sea salt emissions. In the upper tropospheric nucleation plays an important role and a major contribution to CCN by producing up to 60% of the cloud condensation nuclei that originate from upper tropospheric nucleation. While in boundary layer, actually, the number of the contribution of the boundary layer nucleation process is quite small compared to that of upper tropospheric nucleation. So upper tropospheric nucleation is an important process in explaining the abundance of CCN in the boundary layer. So let's go to the campaign data. So this is the MACPEX campaign, the Mid-Latitude Airborne Cirrus Properties experiment that was based at the NASA base at Ellington Field in Houston, Texas, where several flights were conducted mostly in the southern and southeastern US, targeting convective clouds and convective anvil, and also jet stream cirrus. You can see the aircraft profile here, flying from the surface up to about 18 kilometers. So this is in the upper troposphere, lower stratosphere altitude. In April and May of 2011, the scientific objectives of the campaign were to acquire measurements of water vapor at low mixing ratios in the UTLS and to investigate the microphysical and dynamical properties of mid-latitude cirrus clouds and the processes that affecting these properties and their impact on radiation. So this is why we targeted synoptic cirrus and thunderstorm anvil cirrus clouds. The meteorology during this time, this is springtime when we get cold fronts, polar fronts coming from the north, and we have the subtropical and tropical air in the south, and these collide, and when they collide, you get structure in the upper troposphere. So what you see here is a plot of latitude and altitude, and I'm plotting the potential vorticity contours. And you see that as we go poleward, the potential vorticity contours are poleward, the potential vorticity contour of 2 or 3, which typically indicates the location of the dynamic tropopause, is lower. So this is poleward here to the right of the figure. So the front is located at about this location. You see the change in the elevation of this potential vorticity contour, and it indicates that there's a stratospheric intrusion here. Stratospheric air is pushing into the tropospheric air, and there's dynamics occurring here in the UT. Same for this case here on 26th April, the lower figure, we see that as we go from the pole south, we have this tongue of stratospheric air pushing into the troposphere, and this indicates the position of the jet stream and also indicates the position of this upper tropospheric, lower stratospheric air exchange. And this location of the jet stream also indicates the location of these PV contours pushing into the tropospheric air. So this ended up being very important in the analysis of this work in identifying the location of the tropopause. As you see here in the flight 14th April satellite imageries, you see the aircraft targeting jet stream Cirrus, and on 26th April, the aircraft is targeting a mesoscale convective system. So the aircraft sampled outflow of deep convective clouds and jet stream Cirrus each time the tropopause was penetrated. The aircraft was the NASA WB-57, and it has a very good high altitude flight capability. It was heavily instrumented with cloud physics instruments, aerosol instruments, also a suite of water vapor instruments. The instruments that I'm going to talk about today are the NMAS and the FCAS. These were instruments that I had built with my advisor in the lab, and the instruments that he had operated for several years in his group. These are the nuclei mode aerosol size spectrometer, which measures particles, aerosol particles down to 3 nanometers, and the focus cavity aerosol spectrometer, which measures aerosols greater than 100 nanometers up to 1 micron. So the NMAS became very important in identifying new particles. So I'll be speaking about that quite a bit. And the FCAS was very important in measuring the pre-existing surface area of the aerosols, because these act as a sink for the stabilizing vapors that are very important for particle formation. So these were mounted and flown on the aircraft, and the aerosol was sampled through an inlet and flown all the way to 18 kilometers. The NMAS instrument is a system that contains 5 condensation particle counters that are connected in parallel. Each of these condensation particle counters are calibrated so that they can measure aerosols with a 50% cut point of about 5 microns, 8 microns, 15 microns, nanometers, 30 nanometers, and 55 nanometers. Apologies, these are all nanometers. So we can measure aerosol particles down to 3 nanometers up to about 100 by having these 5 condensation particle counters in parallel. So it became very important in looking at the number concentration or mixing ratio of particles in the 8 micron channel, which is channel 2, and the mixing ratio of aerosols in channel 1, about 4 to 5 nanometers, because taking the difference of these two channels will give you an indication whether there's newly formed particles or not, because particles in the 4 to 8 nanometer range would be newly formed particles that have started to grow. So this is exactly what I did in the first step of the work, was to identify newly formed particles by taking the difference between the particles in channel 1 and those in channel 2. So that means the difference between the particles greater than 8 nanometers and the particles greater than 4 nanometers. So if you look at the frequency distribution of the difference of the mixing ratio of these two counters, the counter that counts greater than 8 nanometers and the counter that counts greater than 4 nanometers, you find a tail in this frequency. And this tail is the contribution of the particles that were newly formed. So I developed a method to identify these particles with a high certainty of their occurrence. And this is displayed in this figure. If we see the upper figure from 26th April here, 2011, you have the two mixing ratios being plotted as a time series. So mixing ratio 1 is the 4 nanometer channel, and mixing ratio 2 in the blue is the 8 nanometer channel. And you see that there's certain times when the mixing ratio 1 is higher than mixing ratio 2. So by taking the difference of these two and then doing this relative difference calculation, which I derived to be the method to identify these newly formed particles, you get a excursion in this relative difference. And when this excursion is greater than 3, then it means that that difference is statistically significant. So in this case, you can see that there's one event labeled number 2, and there's another event labeled number 3, where the relative difference is above 3 and increasing. So these are new particle formation events. The rest of the time, you see that the relative difference is right around 0 with some statistical variation due to counting statistics. So identifying the events became very important, and we do this by this relative difference. The relative difference is an indicator of the strength of the particle formation event. So if we look at the relative difference frequency with altitude, we see that there's a band of a high frequency relative difference greater than 3 in an altitude range of about 8 to 13 kilometers or so. So this is the region of the upper troposphere, lower stratosphere. So this is the first indication that particle formation occurs at high frequency near the tropopause. In fact, there were 188 particle formation events identified on these 6 flights that I'm discussing in the study. In addition to identifying the particle formation event, it became very important to identify the tropopause. And I do this by using 2 methods, the dynamic method and the thermal method. The dynamic method I discussed briefly in the beginning of my talk when I was talking about the meteorology, and this is the potential vorticity method, or the PVU. So when the PVU is 2.5, and this was calculated using MAIA reanalysis data, the 2.5 PVU value was an indicator of the occurrence of the dynamic tropopause. Then there was the thermal tropopause, and the thermal tropopause was identified using the WMO definition, which is essentially the temperature inversion that occurs at the tropopause. And these two definitions do not coincide, and the difference can actually has to be explained using other methods. Here we see the MAIA temperature, actually the temperature along the flight track for this particular case on 26th April. So along the flight track, I took the MAIA temperature from the reanalysis data. The aircraft temperature that was measured in situ on the aircraft is in black, and then the MAIA potential vorticity along the flight track is in blue. And I indicate in green the occurrence of the thermal tropopause based on the WMO definition. And I indicate in magenta the occurrence of the dynamic tropopause using the PVU definition. And you see that they don't coincide, but they overlap. So this became quite important to understand the dynamics of the UTLS region. And let's focus here on the bottom figure to begin with. This is a time series of the relative difference. And we see these excursions and the relative difference identifying these particle formation events. So in total, in this particular case, in 26th April, there were about 27 particle formation events. So then we start looking at where they occur. So if we look at the figure above that, we see the mixing ratios of the first and second channel in the NMAS. These are shown in the red and the blue. You also see the cloud top from the satellite imagery and the altitude of the aircraft. And then I have the thermal and the dynamic tropopause being plotted according to the identification I described earlier. But if we focus on the altitude here and the occurrence of the particle formation events, especially the strong ones, we see that particle formation event number 2, for example, occurs when the aircraft is penetrating the dynamic tropopause. See the black line here is crossing the green. And again, when the aircraft descends through the tropopause on the poleward side now, we see there's another event. And then we see another strong event when the aircraft penetrates again the tropopause, and again when the aircraft descends through the tropopause. And these are again shown in these cross sections, these altitude latitude plots of the flight track and these PV contours. And we see here, for example, ozone is plotted on the color plot. We see that the ozone starts to increase as the altitude increases. Ozone resides in the stratosphere, and then there is some high ozone, some low ozone, again some high ozone and some low ozone, indicating that there's mixing here occurring, and also there's this tongue of PV vorticity. So this is the stratospheric air pushing into the tropospheric air. So there's mixing here of the ozone from the stratosphere into the troposphere, and this is also associated with regions of high relative difference, meaning that particle formation is occurring at these locations. So it became very important to look at exactly where the troposphere and stratosphere occur using CO and ozone mixing ratios. So CO originates in the boundary layer and ozone originates in the stratosphere. So if we plot ozone and CO, we see that CO in the troposphere is increasing when ozone is low. And in the stratosphere, we see that ozone is increasing when CO is low. So this identifies the stratospheric pool of air, or the stratospheric air mass, and the tropospheric air mass. So we can, for each of these flights, separate tropospheric air from stratospheric air to start to understand where particle formation occurs. Is it associated with the troposphere? Is it associated with the stratosphere, or something else? And what we found is that there was points that did not belong to these two reservoirs. You have the stratospheric reservoir and you have the polar reservoir, but there were points that did not belong in any of these two reservoirs. And this is called the mixing layer. This is the layer between the troposphere and the stratosphere where the mixing is occurring, and these are the blue lines. So when we look at water vapor, we can see the same thing. Water vapor is in the troposphere, but not in the stratosphere. So we see high water vapor at low ozone and high ozone at low water vapor. And again, we see points that don't belong. Actually, these points are along a line indicating that there's a mixing between the two. So there's a layer between the troposphere and the stratosphere, which is a mixing layer. So if we plot the tropospheric points and the stratospheric points, using as a coordinate the altitude of the measurement that's being made by the aircraft subtracted by the dynamic tropopause. We see that the dynamic tropopause separates very nicely the tropospheric air from the stratospheric air when it comes to CO, ozone, and water vapor. When we use the thermal tropopause, the WMO definition of the tropopause, we see that there's not a good separation. So the dynamic tropopause is a better definition in terms of chemistry that is occurring in the upper troposphere and lower stratosphere. When we look at this mixing layer, we see that this occurs around the dynamic tropopause and also around the thermal tropopause. So the mixing layer may be associated with both of those processes. When we look at particle formation, where it occurs, so these black data points are the data points with particle formation. We see that particle formation is mostly confined in the troposphere, but also in the mixing layer and sometimes into the stratosphere. So now we ask the question, where does it really occur? So taking the size distributions from all these data, we have now data from the upper troposphere, which are plotted here in the lower graph, data from the mixing layer in the middle, and data from the stratosphere, which are up top. And what I've done here, I've taken all the size distributions measured in each of these layers, and I've done various averages of those data. So we see that upper troposphere with no new particle formation, we have a size distribution as follows, while upper troposphere with particle formation looks somewhat different. One of the differences is that we have newly formed particles in the nucleation mode here of the size distribution, smaller than 0.01 micrometers or 10 nanometers. We also have fewer aerosols in the tail end of the size distribution, meaning that the surface area is much less. So we already have an indication here that when we have particle formation, we have a smaller surface area. We have fewer particles that are larger. In each of the size distributions with particle formation, we see a nucleation mode, while in size distributions with no particle formation, we have fewer particles in the nucleation mode. And to describe this a little bit more succinctly, you can see the data now overplotted. So in the mixing layer, for example, the size distributions with particle formation, you can see that there's many more particles in this nucleation mode when particle formation occurs compared to size distributions with no particle formation. So summarizing the data in a different way, in this case, I'm trying to understand the frequency of particle formation in these layers and what might be the cause for this particle formation. So if we start from the left here, this is the middle troposphere and the upper troposphere. And we have the frequency distribution of particles with particle formation and the frequency distribution of all of the data. So we see that in the upper troposphere, the frequency of data points with particle formation are quite high in the upper troposphere. Let's say -4, the dynamic tropopause. So down to -4 kilometers down from the dynamic tropopause. So 4 kilometers below the dynamic tropopause, we have a high frequency of upper tropospheric nucleation. In the mixing layer occurs around the dynamic tropopause. We have regions with high frequency of particle formation. While in the stratosphere, which is above the dynamic tropopause, we have very few particle formation events. Only near the lower levels of the stratosphere, we have a high frequency of particle formation events. Here we see that we identify a jet stream in the mixing layer. And this is important because there may be a dynamic effect associated with the formation of these new particles. And in this next figure here, panel E, I'm plotting the mixing ratio of CO. And we have CO in the troposphere in black, CO in the mixing layer in blue, and then CO in the stratosphere in red. What's important here, we see CO mixing ratio greater than 100 parts per billion in the lower to mid troposphere. But look at the mixing layer and the upper troposphere. We see high concentrations of CO that are comparable in value with those measured in the middle troposphere. This means that there is a process that's moving the CO from the middle troposphere to the upper troposphere and the mixing layer. And we think that this is associated with clouds. It's not shown here, but whenever CO was high in the upper troposphere and the mixing layer, the distance from cloud, the aircraft distance from cloud, was small. So we think that the CO was high near cloud. We also see that the number concentration of small particles and the fraction of small particles compared to the total number of particles, it has an interesting trend. For example, we see that in the upper troposphere and the mixing layer, there are regions where the number of small particles compared to the total number of particles is significant. And the significance of this is related actually to the surface area. So there are regions where there's high concentrations of small particles that are also associated with high concentrations or variability in the surface area. So this became a little complicated to untangle. And I had to separate the convective cases from the jet stream cases because dynamically these clouds are very different. The jet stream clouds are dynamically more stable and less turbulent than the convective clouds. So what I do here, I understand this figure is a little bit difficult to understand, but I relate all these parameters, CO, distance from cloud, surface area, and all the parameters of the size distribution. For example, this parameter here is the number of small particles compared to the total number. How these vary in the jet stream cases and the convective cases when particle formation was present and when it was absent. And what we found is that the particle formation was related to surface area, as all new particle formation cases had a lower surface area when compared to non-NPF cases. So the surface area is extremely important in the upper troposphere, lower stratosphere in determining the intensity of the particle formation event and whether the particle formation event proceeds. We also notice a signal in the small number of particles when it comes to convective clouds with particle formation. In this case, we have ultrafine particles present in the proximity of convective clouds, and these occurred when particle formation was present. In the upper troposphere convective cases, we noticed a higher concentration of CO and larger surface area. So we see here in the convective cases, we have higher concentrations of CO. So this means that the convection is bringing the CO from the boundary layer into the upper troposphere and the mixing layer. And it's also causing the surface area to increase. So there's a process there where aerosols are present and increasing the surface area near clouds. In the upper troposphere, surface area suppressed particle formation, but nucleation still occurred. So even though the surface area was high near clouds, the CO was so high. Now, CO does not cause particle formation, but there may have been other trace gases, other stabilizing vapors mixed with the CO originating from the boundary layer that could have stabilized the particle formation process. So CO is being used as a surrogate for boundary layer vapors in the study. So to explain this further, I used a model called MAIA, Model of Aerosols and Ions in the Atmosphere. And this is a model written by Jan Kaziel at NOAA. And he graciously allowed me to use this model to simulate these particle formation events. And what I did was, wherever there was a particle formation event, I used that size distribution that was measured and then used the model that simulates this binary nucleation process to calculate the evolution of that size distribution to determine whether cloud will form. And these are some results from the model. And I'm not gonna go through this, but high split was used for forward trajectories, mainly for the pressure and temperature data. And then the cosmic ray ion production rates were calculated. And this is important for the estimates of OH, which are very important for binary nucleation to occur. So when we look at these modeled size distributions, which are shown in the plot, in the lower plot here, so this is the particle formation event, and this is the measurement that was made at time 0. And then the model calculated the evolution of the size distribution. And you see here these particle formation events that are being simulated by the model. Here you have clustering at the sub 1 nanometer size, but no growth. But over several days, you see that when we have particle formation in the beginning of the simulation, we end up with a size distribution that has a fairly high concentration, greater than 50 nanometer in size. And 50 nanometers and 100 nanometers, these lines that you see here, are used as surrogates for the cloud condensation nuclei, because at 50 nanometers, these particles are large enough to be able to act as seeds on which clouds can condense on. So after a few days, particle formation can lead to these particles becoming CCN. So starting to close the picture on this study, we found that in the upper troposphere, new particle formation was suppressed and limited to the first 24 to 48 hours into the simulation. So we see here the first 24 to 48 hours particle formation here is occurring, but then later than that, it is suppressed. And that's because the particles are growing and their surface area increases. So the sulfuric acid condenses on these particles rather than contributing to the formation of new particles. So there's a large sensitivity of this surface area condensation sink, which is very important in this process. In the upper troposphere, new particle formation occurred almost 30% of the time over the 4-day period of the simulation, compared to twice that amount of time in the mixing layer. So both the upper troposphere and the mixing layer are very important, as indicated by the simulations and the formation of these particle formation events and their growth. In the mixing layer, particle formation events were of longer duration and higher intensity. In general, nucleation was suppressed by high surface area, but in certain conditions, the particle formation still proceeded. So that means that the vapors were sufficiently high in concentration. In the simulation, the increase in CCN was significant, but it was very dependent on the concentration of SO2. So I got the SO2 data from another campaign. So I used various thresholds of SO2 in the simulation, but these SO2 values are relevant in the region. These are not exaggerated values. So this indicates very clearly that particle formation is a significant source of potential cloud condensation nuclei, at least in the mid-latitudes. NPF events in the upper troposphere and the mid-latitudes were frequent in this campaign, and these are going to impact the CCN concentrations. What's important here is that these were linked to convective cloud outflow, and this link is most likely attributed to the ejection of high concentrations of SO2 and DUT. Now, we did not measure that, but we measured CO. And the hypothesis here is that CO and SO2 are both originating from the boundary layer. So if the condensation sink does not increase over time, you could get CCN concentrations that are sufficiently high in concentration, and the size of the aerosol is sufficiently large for them to impact clouds. So moving to another campaign, this ATOM mission, what you see here is flight wrecks in 2016 and 2017 in the Pacific and the Atlantic. And you see the aircraft ascending and descending from pole to pole using the same instruments that I just described. And from those data, summarizing the whole campaign, actually, you see that there's a very interesting trend in the size distribution. So these are data from the UHSAS, the ultra-high sensitivity aerosol spectrometer greater than 60 nanometers, which is this white line. And then below that value, below 60 nanometers, is data from the NMAS, this instrument that has 5 CPCs in parallel. And we see here there's in the upper troposphere at 300 millibars and above, we see that there's this intense nucleation mode that is occurring. And this is attributed to new particle formation. So this is a campaign average that you see here. And this was also explained by the models. So panel B is the modeling, panel A is the observation. So the modeling can explain this particle formation process in the upper troposphere. So that means that we have started to understand the physics around this. So new particle formation is relevant and important in the upper troposphere. These newly formed particles grow to CCN active sizes during descent into the boundary layer. Current models underestimate CCN in the boundary layer because they are not accounting for upper tropospheric nucleation contributing to this process. So in summary, this is the paper that we started with, and it's the paper that we'll end with. We have contributed in the understanding of this process on how particle formation in the upper troposphere contributes in producing these seeds, these seed particles, to add aerosol mass in the boundary layer and seed clouds in the boundary layer, which could be relevant in certain regions. In certain regions, when we have persistent stratocumulus clouds, like in the Southern Ocean or in the South Atlantic, there's bands of persistent clouds where the source of CCN is negligible. So where do the sources of CCN come from? And the first image that I showed you in the beginning was this modeling study from Leeds, where 60% of those CCN at 0.2% supersaturation appear to come from upper tropospheric nucleation. But the process by which these occur is somewhat mysterious. So I think we have contributed here in a significant manner in understanding how deep convective clouds loft these precursor gases from the boundary layer into the upper troposphere. This helps to stabilize the vapors in the upper troposphere, where the dynamics of the mixing layer in the upper in the tropopause and the stratospheric mixing region, the cold temperatures and the high abundance of SO2 and the low concentration of pre-existing aerosols help with the particle formation, with the binary particle formation process to proceed. And then the models have given us sufficient information to describe how these particles grow and then contribute to become large enough that they may be acting as CCN. So I will end this here now and open for questions. We have a few minutes left, and I'll be happy to stay as long as you desire to answer questions.
Thank you, Dr. Duncan. You have nicely illustrated the formation mechanism of new particle formation in UTLS region in mid-latitude by combining the synergized aircraft and model simulation results. So it was very nice, and you timely finished it. So I think we will definitely have some questions from the participants. So I request all participants to one by one raise your question, and you can also type on the chat box so I can put forward to Dr. Duncan.
I have a question. So can you hear me?
Yes.
Okay. So among the three altitudes, like upper troposphere, and then mixing layer and the lower stratosphere, if one has to quantify from your campaign, then is it possible to put some numbers like percentage, how much of the CCN was formed within the upper troposphere, and then how much, and then whether there was a formation, new particle formation occurred in the stratosphere, or it has just, through exchange, it is moving from troposphere to the stratosphere, unlike the beryllium-7, where we see the stratosphere to tropospheric exchange. Here, do we see troposphere to stratosphere exchange?
That's a very good question, and it appears that several situations have to occur. You have to be in the mid-latitudes. It has this process in the convective cases was associated with mesoscale convective systems. And the anvil of these clouds typically occur just below the tropopause. Now, that's probably the thermal tropopause, but the dynamic tropopause is helping that process because of this mixing, this stratospheric, tropospheric mixing. That was also present in the jet stream cases, but in the jet stream cases, the particle formation intensity was much less, which means that the number of newly formed particles would be much less. So in terms of CCN contribution, which is your question, I would say that the clouds are extremely important, as shown in this picture. The clouds are extremely important. So the presence of clouds would be the most important phenomena that would determine the location of these formation events. And then the location of that anvil. So the anvil typically is on the downwind side. So it would be downstream of the jet stream location, downstream of the trough of the jet stream, coincident with the cloud location. So you can kind of picture that, and I would say from the information that we have that that's where the high intensity formation events will occur.
So one question is like, do you see NPF in the lower stratosphere, or it is only through the mixing layer? What do you say?
According to the frequency distribution, it appears like particle formation events in terms of their occurrence were limited to 4 kilometers below the dynamic tropopause. So below the dynamic tropopause, so that's defined as upper troposphere. Then in the mixing layer, which was around the dynamic tropopause, and then in the lower part of the stratosphere. So I would say that it's from 1 to 2 kilometers above the dynamic tropopause up to 4 kilometers below the dynamic tropopause. So you have a band of about 6 kilometers, mostly in the mixing layer and in the upper troposphere.
Okay, thank you.
Any other questions?
So
Sir,
there's
chat.
Yeah, go ahead.
I posted in the chat.
Yes, the question is, you mentioned you didn't get the concentration of CO or sulfur dioxide. Was it the limitation of the instrument or a specific reason? Can you give an insight on what mechanism the NMAS instrument uses? So let me answer the first question. The CO, we did measure CO. So CO was measured, sulfur dioxide, SO2, was not. And the reason for that was the instrument works very well in the lower atmosphere, in the free troposphere, but in the upper troposphere, this is a very challenging and measurement to be made. At 18 kilometers, using a trace gas analyzer, it's a bit difficult. There are instruments that measure SO2 at this high altitude, but they're very rare. So that is the reason why. It was a payload availability. The instrument was not available. CO was measured. The NMAS instrument is shown here, and I did not discuss this in detail, but this is a instrument developed at the University of Denver, and it is a condensation particle counter. Actually, it's a very simple instrument, but you have 5 of them. So if you use a differential mobility analyzer or a scanning mobility particle sizer or a particle counter, it has one of these components. It's called a condensation particle counter. And what it is, it's a bath of liquid. Typically, it's butanol, some type of alcohol. In this case, it's fluor inert because of the challenging environment we're working in. And this alcohol is maintained in a bath, and the aerosol flows over that bath. And the aerosol will take up the vapor, and it will grow to a very large size where it can be measured very easily. So the aerosol, which is very small, is very difficult to measure optically. So you need to grow it to a large size so that you get, when you shine a light on it using an instrument, you get a large signal. If you have a small aerosol particle, you shine a light on it, you're going to get a very small signal, which means that you can't measure it easily. So one way is to condition the aerosol, meaning you're changing its properties. And the way you do that, in this case, is you grow it. So you're growing it to a very large size, where it becomes a droplet, and then you measure the droplet, and you count it. So the size cut here is very critical, and that's done by controlling the temperature at which this condensation process occurs, and determining on the temperature, how accurately you maintain that temperature inside the instrument, it determines the cut point. So we talked about channel 1 and channel 2. Channel 1, here you see the growth efficiency. You see that growth starts at 3 nanometers, and by 20 nanometers or so, you've grown all the particles at that point. So channel 1 will grow all the particles greater than 3 nanometers. Channel 2 will grow all the particles greater than about 6 nanometers. So the technique here was to use this channel and this channel and assume that new particles occur in between. And by subtracting the concentration of these two channels, you're identifying the newly formed particles.
Okay.
So, Dr. Duncan, there is another question in the chat box.
Why CCN is enhancing the precipitation in case of cloud seeding, whereas it's delaying the precipitation in the case of aerosol cloud interaction? So this is a very interesting question, and we could have another talk on this actually, because it's very complicated to answer. But it depends mostly on the size and the chemical composition of the aerosol. It also depends on the number concentration of the aerosol. So this is all based on the Toomey effect, and for the most part on the Toomey effect. So the Toomey effect states, what Toomey discovered was that if you have a cloud of a fixed liquid water content, if you introduce a low concentration of aerosols, then you're going to condense that water on a small number of aerosols, which means that those droplets that form, those CCN that form, would be quite large in size. On the other hand, if you introduce a high number of aerosols for the same amount of liquid water, now that liquid water has to distribute over a higher number of seed particles. So what happens is that your droplets that form by the liquid water condensing on those particles, those droplets would be smaller in size. So in terms of aerosol cloud interaction, the fundamental of aerosol cloud interaction is just that it depends on the aerosol number. So pollution releases a large number of aerosols, and these aerosols can distribute the liquid water amongst many particles, so you get smaller droplets. What that might do, it may delay the onset of precipitation. So that's what you're mentioning there, the delaying of the precipitation in the case of aerosol cloud interaction. Very smart, very nice. In terms of enhancing the precipitation in case of cloud seeding, now we have picked the aerosol. The aerosol is engineered. That means that we know its size, we know its chemistry, and we know its CCN activation properties. And what we do is we insert that engineered aerosol in places where it could be beneficial, meaning in places where the aerosols, for example, do not have the correct chemistry or do not have the correct size. So in regions that, for example, are highly polluted, if we insert larger aerosols that are more hygroscopic, they take up water more readily, then the water will condense on these aerosols, on these seeding aerosols, versus the pollution ones, to form larger droplets, which may enhance the precipitation. Now we're simplifying the physics here greatly. The physics that I just mentioned is simplified. And this is why we study cloud seeding before we implement it, because it depends greatly on the aerosols that are already existing for cloud seeding to work. That was a very nice question.
Any other questions?
As we see at polar front jet stream, winds are having high speed, but as you mentioned in your talks, that during measurement of aerosols present in the region, jet stream clouds have less turbulence. Yes, so the as we saw in this potential vorticity advection, where we have this stratospheric air penetrating the tropospheric air, this occurs in the region of the jet stream, and there's a lot of wind shear there. Not only high winds, but there's also wind shear, very drastic changes in the wind velocity across that jet core. So the particle formation was present in the region of this jet stream, but that part of the process I don't understand very well. I have a hypothesis on this, but I don't understand why the particle formation preferentially occurred in the region of this mixing layer, which is associated with the jet stream. So I can't answer why the aerosols form in this mixing layer. I have some hypotheses that I've written up, but in my thesis actually, but this is not well understood.
Yeah, and one question also I had, as in the convective cloud system, there, as you said, the ejection of the sulfur dioxide is more than we expected.
Could you write down, because your voice is not very clear? Could you please write down in the chat?
I think the question is related to CO2. I'll wait for the question here, but I think it's related to the CO2 being present in the upper troposphere. This is due to the process of the cloud acting as a chimney, so to speak, where the convective clouds, the cloud bases have updrafts in them, and the material in the boundary layer is going to mix. And the CO is the trace gas that we measured, but obviously there are other gases that that exist in the boundary layer. So these gases are entrained into the cloud using the updraft, the thermal, the updraft. And within the cloud, these gases are being lifted. Now, there's a problem here because some gases are soluble and they will reduce in concentration within the cloud. But some are sufficiently high in concentration that they will survive, and some are not impacted by the cloud. So they will be lifted up and then ejected out of the anvil, which is the outflow, the main outflow of the updraft of the convection, the main outflow, this Siderus sheet coming out of the convection. This is all outflow. So all that gas that was being entrained within the cloud is ejected. And then there's high concentrations of these gases in regions that they do not typically occur because they do not form there. And these gases are studied because another thing that is present in high abundance in the upper troposphere is OH, which is very important for reactions to occur. So once any of these gases are there, then reactions start occurring. And these all lead to the formation of vapors that act to stabilize the particle formation reaction. So these vapors are extremely important, and they could be organic vapors, they could be ammonia, high concentrations of water vapor, and some unknown vapors as well that could stabilize these reactions.
Any other questions? So if there is no question, then let us thank Dr. Duncan once again for his very informative talk. And I'm sure that all participants, so those who attended this webinar, might have benefited a lot. So thank you, Dr. Duncan, for having accepted, having agreed for this webinar and sparing your valuable time. So I hope to see you soon when you are visiting India in IST, and we'll have your presence in IST and have another talk when you are physically present in IST. So thank you very much for having such a wonderful webinar today.
Thank you for your attention. It's always my pleasure, and I also hope to be there very soon. I'm actually quite anxious to come. Actually, my last travel for 14th March, I was in Delhi leaving because I had to start my way home because all the flights were being canceled. But the last place I was in India before I stopped traveling. So I hope to make it my first when I start traveling again. Thank you, everybody.
Thank you. Thank you. Thank you very much.